Okay, welcome all of you to the first live session of this term's offering of the course Neural Networks for Signal Processing. I'm here with my teaching assistant Amrita. So we are happy to take any questions. So feel free to post your questions that are pertaining to the topic and relevant to this course, and would be happy to take any questions. Amrita, we might be having a few questions already, right?
Yes, sir.
Okay.
So the first question is by Kamalakannan Subramani.
Okay.
So he says that I'm astonished by the role of activation function in introducing the nonlinearity in the system, which when scaled properly by the synaptic weights makes the neural network to learn any function. I'm wondering, especially after watching your lecture on bounds on approximation error, what if we use complex exponential as an activation function? Does it bring any advantage with it? Is there any neural network using such activation function?
Okay. So I think the answer to this question would be in two parts. So the exponential doesn't satisfy some of the properties that we have for activation functions. For example, there is no saturation that is happening. For example, if you look at the sigmoid function or the rectified function, etc., there is this clipping, inherent clipping that is happening with these functions, and that is not there within this exponential. Second, you want to weight with a complex exponential, and you see if it is a better fit, right? I mean, I could see this, that there is a phase, there is also a magnitude in the expression of the complex functional, but you can always learn the arguments in the real part and the imaginary part, or in fact you can learn the phase appropriately within the neural network. So there is no reason why you have to go with this functional form. But I suggest you experiment with it and see how good this is in terms of approximation. But I think standard functions which have a certain linear region and those with saturate and have good differentiable properties are those preferred in terms of activation function. And these also have they draw inspiration from neurobiological plausibility, right? And that's the reason why we want to bring in these sort of activation functions than the standard exponential function, which defined over orthogonal supports can also be expressed as a basis in some sense. Okay.
We next have a question from Pavan Tripathi. I recently came across the expression of probability of finding an electron in an energy state. This expression is similar to the logistic function in neural networks. So the question is that really a coincidence, or is it that nature follows logistic function and hence events happen? Or if it is in the nature, then the data generated tends to follow logistic function for classification.
I think you have a good question. I think this is more a philosophical, the answer to this is more philosophical, right? We don't know how nature works. Let me put it very precisely. Because we are looking into building mathematical models that basically fit empirical data, right? If the form of logistic function can fit a certain expression of nature, or in the sense what we observe in from empirical studies, then it's a good fit. But does nature really work with this particular model? I don't think so, or there is no precise answer to this, right? And the second question is, there are models, probabilistic models. There are different forms of assumptions that we make with these models, and what model is suitable for a particular data has to be really explored, and it is basically a subjective problem, right? So it is a coincidence that you find logistic function in both these realms, but I don't think you can say that nature works because of logistic modeling, etc. No, it is not. And it may be a simple model to sort of mimic the behavior, or at least explain some empirical observations that we see in nature. I think that is what is my perspective. Right? We don't know how nature works, so it is important to model, and no model is a perfect reality.
We next have a question from Noel Solanki.
Okay.
For the assignment problem solving, which book can be useful?
Good question. So we basically give problems what comes into our mind at that point of time, depending upon the course contents that we have created, right? So I think there are a few good books. For example, Hakin's book, Neural Networks and Learning Systems, there are a lot of exercise problems. I suggest that you try and explore some of these problems. And we have listed 4 to 5 reference books on the website. So you can take a look into these reference books, particularly on the exercises component, and then try to solve some of the problems. Right? I think that can help you out. Other than that, we don't have a list of problems that we can a priori publish, right? So if and this is the first time offering of this course, but I would also encourage you to look into my web page where this course is listed, where I've taught this course a couple of times, and there may be some homework problems there, and you can look into those problems, and if there are any solutions posted there that can help you towards gearing up for your assignments through NPTEL. I hope this answers your question.
We next have a question on the live chat. We say that neural networks are non-parametric, but we people say that the weight matrices are the parameters of the networks. How is that possible?
Okay, Malay Guhan. So to answer your question, see, when we think about parametric and non-parametric forms, when we think about parametric forms, we think that the underlying parameters within the probabilistic model is known, or we know the density, for example, the probability density function, or we know the properties of the random process, for instance, and there is a certain model and certain variables that are associated with this model that we can estimate, right? And that forms parametric. That is the form of parametric models. In the case of neural networks, we do not assume any parametric form for the underlying probability model or the random process, etc. Right? And we try to derive these parameters through the neural network. And the only parameters that we have within this neural network are the weights and the activation function, etc. So in that sense, you can say it is parametric with respect to the model of the neural network, but it is not parametric with respect to the underlying probabilistic model or the distribution. So I think that clarity is something that I would like to bring through this forum. Okay, I hope this answers your question. So I have this question from Pawan. What is the link of your web page? So Amrita is just typing this up. So you will get this answer in just a few seconds, possibly. So you go to pnsil.desc.iisc.ac.in and then navigate through the teaching tabs, and there you will see this neural networks for learning systems or signal processing, one of the 2 avatars that are listed there, and that can help you see through the assignments that we have offered at ISC. So unfortunately, we cannot give you too many computer-based assignments that we can grade like the way we do here at ISC, right? So, and I hope that you do this, that you build the code yourself and exercise through the data sets, and that's the best way to learn this course along with the theory. Okay, I hope this helps.
So we have another question. Do neural networks have multiple local minimum for the loss function?
It depends on the loss function that you start with. It depends on the objective, right? If you think about having the maximum likelihood function and then you want to, learn the parameters with respect to this function, then there is no unique global minima that you can compute offhand, right? You'll have to basically do some annealing, and then you'll have to do gradient descent along with annealing in a way that you can cross several local minima and get to hopefully a global minima, right? So it depends upon the terrain. But if you have a nice convex function such as a quadratic, etc., then you can optimize, and you can exactly get to the saddle point of the surface, right, of the objective function. So it again depends upon how you set up the objective function and what you exactly want from the loss function or the objective function, right? And it is something that is a choice of the designer building this network. I hope this addresses your question. So how many people are there live? 8. So feel free to express yourself. It can be a simple fill it out or to some clarification that you need from the slides or anything. We are happy to take your questions. So we have another question here from Malay Guhan. How to classification different from regression?
I think his question is, how is classification different from regression?
Well, you regress on the data. That is, you basically fit the model when you regress on the data, right? And the outcome of the regression can also be used for classification potentially, right? You have certain labels associated, and then basically when you do the regression modeling, you extract the parameters, and then you you have a data, and then you feed this back to this model, and then it can give you a certain outcome, right? And that's what we saw with the logistic regression, etc., and useful for prediction. But you can also have a classification problem where you train a neural network to learn these labels. That is, you associate the feature with the outcome, and you learn these mappings, and that's a classification problem. So I think they are linked, they are related in a way. In one side you assume a certain model, and then you basically regress on that using the data. You regress on the model and extract the parameters out, and then use that basically towards your prediction. In the other case, you have the xy pairs, and you want to figure out that function that associates x with y, right? These pairs, and then that's the way you proceed with a neural network architecture. Okay, I think that's the philosophy. Yeah. So there's another question from Anil. Thanks for reducing my fear about learning neural networks. I'm glad that you are not afraid of this anymore, and that you are a beginner. There's a beginning to everything, right? So initially, when you see anything, any course or any new material that is unfamiliar with, there is always a fear or also inertia or hesitance. But I think you start working through the details, and you learn, you will be okay with it. So I'm glad that you are finding this interesting. So please leave your likes on the videos. Leave your comments. Though it's impossible for us to address all the questions that we see on the YouTube videos, at least if you join us for live session, it is easier for us to talk about. Yeah.
So we have another question Do neural networks perform better than SVM and decision trees?
I think this is, I think not, it's a question which is vague, right? So SVMs are also, we consider it part of statistical learning machine. Perspective decision trees also are part of this category. A neural network, as I told you, right, it is also a learning system. It's a statistical learning machine, right? So saying that this works better than the other. See, for example, if you think about SVMs, you have this linear. If you work with linear decision boundaries and you get to higher decision, higher dimensions, where you can work with linear decision boundaries, and that's the philosophy, that's the guiding model. But there's no reason that you have to go to higher dimensions and think about linear, linear decision boundaries and basically for classification purposes, you can think about non-linear decision boundaries, and for which neural networks can help you. And both are statistical machines, they play with data. And what is good or what is bad, you have to basically put these metrics, such as how easy in terms of the spatial complexity and the time complexity of execution of the algorithm, both during training and testing, right? The time and space complexities of the algorithm, then the fundamental limits on the models themselves. So therefore, I cannot answer your question, because if you are having a sort of data which works with good linear decision boundaries, such as the perceptron or maybe an SVM, in that sense, why should you build a complicated neural network to do this task, right? And for sometimes you may not be able to visualize this geometry in higher dimensions. It may be difficult to picture that, and in such situations, feeding this data to a neural network can help you get your results. So I think it is speed, accuracy of results. So the accuracy is again subjective depending upon the data sets and what works best in terms of your bounds, in terms of time-space complexities and fundamental limitations with the algorithm or the probabilistic model and the approach of the statistical machine itself. Okay.
We have another question. Please put some light on activation functions.
Okay. So, I mean, the activation function in neural networks is sort of akin to the basis functions we see in traditional signal processing, right? I'm not saying it's a one-to-one correspondence, but it is like the basis function. For example, I give you any signal in a signal space, and if I know the basis of that signal space, I can represent the signal using this basis up to a certain approximation error. So the same idea is sort of endowed within a nonlinear signal processing framework using neural networks, right? So the universal approximation theorem guarantees that if you have activation functions like these which satisfy certain properties, you can approximate any function. It doesn't talk about any space complexity, right? I can have a hidden layer and I can have infinite neurons within the hidden layer, and given this is enough. If I have an input layer, an output layer, and a hidden layer with possibly infinite neurons, I can approximate these functions. So therefore, it is in that sense universal approximation. Can we use neural networks concept to study? See, fractal has a very interesting geometry to it, right? I mean, it is an infinite area with infinite perimeter or something like this. I mean, it's self-containment. Containment of one. Having this fractional dimension. For your space, and then self-similarity property that expresses itself. So there is a nice way you can that is rich mathematically, that you can express a fractal. So why even go towards having a neural network to create this curve? I mean, you can create such curves. It is possible, but why have a sledgehammer when you have a nice tool using the fractal itself that you can express it very elegantly mathematically? So I don't see your roundabout use of neural network to study fractals. Possibly not. May not. I mean, if you didn't know the functional form, then yes, I would say just go with a neural network because you don't know what to guess. But a fractal is a nice, it has a nice structure. You know how your Koch curves work. You know how your Mandelbrot sets work, right? I mean, you know the functional form of these. But if you want approximate, yes. You know you don't know the functional form. Feed this, extract all the relevant features, and feed this to your neural network. Hopefully, it will construct a good curve for you. Okay. So I hope it addresses your question. But I don't still see the motivation for you why you want neural networks to study fractals.
Next, we have a question. Can we implement Rosenblatt's perceptron using logistic function as an activation function?
I mean, see if it is. See, Rosenblatt's perceptron is it works on linearly separable patterns, right? And you don't have to bring in a sophisticated neural network to model this because it is linearly separable. But you don't know, for instance, there are certain cases where, for example, you cannot visualize if it is linearly separable or not. In such cases, just feed this to a perceptron. If you have a perceptron that you have automated, feed this data, and then if it is linearly separable, you will be able to see the boundary. So you don't have to bring in a logistic function as an activation and then bring this up. But if not, yeah, you can bring a logistic function or a sigmoid. Typically these days it's common to have rectified linear units because of the problem with the vanishing gradient problem, right? So therefore you can use this simple rectified linear unit as the activation, and then feed that within a neural network. And if it gives you linear decision boundaries, great. You know you have the separability already. Instead of having a curve as your discriminant boundary, you already have a line there. So it is possibly simple. Okay, Anil has this question. Doesn't so I don't know what is your source for reference books. Look through any public library, look through any university web page, look through Google Books. You can buy those if you have. Sometimes you get electronic books that you can download, that or with a small payment of money you can download these electronic books onto your Kindle or whichever electronic book that electronic platform that you want to download these books. So I believe it to you, but these are in general you can find them. Okay, so the next question is, can you explain likelihood function in simple words? Likelihood is odds against one event versus odds against another event. For example, what is it that I'm going to win this football match given that it is raining versus I don't win, right? I win versus I don't win. The odds against. So that is basically the likelihood is basically what is the likelihood? I mean, what is the probability? Odds against something. So that's so when you define a ratio of these odds, a likelihood is a probability, and when you take the odds of one event against the odds of another event, then you form a likelihood ratio. And when you take the log of this likelihood ratio, that becomes a log likelihood ratio, right? And particularly for binary hypothesis testing and binary kind of hypothesis where something is 0, something is 1, this log likelihood makes sense. If you cannot bring in a binary hypothesis and it can have multiple labels, then you have to align with respect to a reference label, and you can still do that. And that's what we dealt with in multiple um, regression, multiple logistic regression, and some of these ideas that we talked in the slides. Okay.
The next question is, can you differentiate between stochastic gradient and the stochastic gradient with momentum?
Okay, see, stochastic gradient comes as a natural gradient that you take with respect to the objective function, right? If you take the gradient, I take the gradient of the cost function, you get a result, right? And that's a natural gradient that you have. But we can tinker this natural gradient heuristically by introducing this moment. It is a heuristic rule that you have to bear in mind. You give this momentum, and this momentum helps to basically accelerate your convergence, etc. Right? So you may also ask this question. I would ask this question from research perspective. Suppose I start with the learning rule itself, that I start with this gradient descent with this momentum. Can I set up my cost appropriately? You can pose that question and you can think about it. Right? I will leave this as an exercise for you to sort of think slightly differently. But in general, sometimes you arrive at the gradient descent based on a textbook way of arriving at the gradient, and you see that that may not be working very well in terms of your convergence, because the rate of convergence is also very important when you discuss algorithms, right? That means how quickly you're diving down in your error space, right? So therefore, you may need to bring in this momentum term where you slightly accelerate that process, and that's the idea there, and that's the differentiation.
So we have the next question. Is part 2 and part 3 of this course in line next year on SWAYAM or NPTEL?
Not immediately. It's a good question. So are you a graduate student, Pawan? Can you tell me your background? What is your background? Are you a graduate student or self-employed or employed? That you need parts 2 and 3 immediately? So you can write it up in the text. It doesn't matter. So it's a lot of effort for us when we design these NPTEL courses. Um, I mean, I would say that it is the content that we have is really almost like two courses, content from two courses that we put in, and we don't want to sacrifice the quality of the courses that we offer. So definitely yes, we would like to offer part 2 and part 3, but it will not be immediately next year, because we have the content, but it has to be polished. We have to figure out all the nitty-gritties to get these recorded. Um, but it will be offered at some point of time, but not be immediately following next year. Right? We would like to run and dry run this course few times and exercise this so that it is beneficial to all the people in the country and outside the country. Um, and based on these feedbacks and knowing your limitations, we will bring in advanced topics, that is parts 2 and 3 of the course. So I see your background. You're an electronics engineer and you want to make a career in AI, preparing for GATE now. You're welcome to IISc, or I mean, of course, I'm from IISc, so I welcome you to IISc. So any other institute that offers this course, of course, you would like to make your career. So you can prepare for your GATE. Certainly, neural networks is one of the basic courses for. I mean, it's I think the building block for AI. I mean, if you're talking about AI, then you should be knowing neural networks for sure. So you're encouraged, to learn the material from the course, and then I would like you to apply to Indian Institute of Science, and if things work well, you will land up into the program, and you can work with me or any other faculty member associated with the AI program. So I hope this addresses your question. Yeah. Do you have more strength now in terms of students, or
11 students.
11? Okay. So please leave your likes and comments on the YouTube videos, and that's a good way that we can get feedback, saying that, and if you have any questions, you can always bring in this to the forum, or you can ask questions at YouTube as well. I always wonder how mathematical concepts apply to predict things. Well, I would say the modern mathematician, or who uses these tools for decision making and prediction, is like the astrologer's job 200 years back, or even 100 years back, except that you're more well informed. You have you extract the right kind of parameters, and you have the right features, and you use these features to learn relationships, right? And that has to be learned mathematically, because any rule that you think a human does, you have to make a machine learn, and therefore you have to bring in these ideas of correlation and associations that are driven by clear mathematical concepts and algorithms, right? And I think you would have seen, for example, when you work with the the backpropagation algorithm, how the algorithm is constructed in the first place, how you learn the inputs and the outputs, and how the mapping is built, right? And that's the first exercise to see how you can predict, right? I mean, you learn the mappings and then you give an unknown feature set, and then you get some outcome from the network, and based on that you can basically predict, and this is how it works. So, and depending upon how you want to make your model sophisticated, like bringing in memory, bringing in feedback, and all kinds of configurations, you can make the models more sophisticated, basically to drive things, essentially to predict, learn mappings, um, etc. Right? Recognize things, etc. Yeah.
The next question is, do decision changes with activation function?
The decision is the same, right? Why do you want to change the activation function? You fix the activation function throughout your learning process. You don't change the activation function. So you're given the inputs and you're given some outputs as part of your training set. You fix the activation function and you learn the mapping, and then you give an unknown data to the network after you've learned things through training, and the network, based on the same activation function, predicts something out as your outcome, and you have to do whatever you have to do with this outcome, right? And if you've learned pretty well, then on your test set, assuming the test set is part of your, is like, has the signature of your training set, it gives you, what decision you want with zero error, right? Otherwise, if the test set is vastly different from the training, then yeah, your decision can be different, for which you have to basically get the variability into your training set. That's the reason why you have all these cross validation and these strategies, so that you divide and conquer your data sets, and then learn these things. Yeah.
I think the question is, say you use tan H activation and compare it with the result you get with ReLU.
Okay.
Would the decision, would the neural networks
It,
be two different?
yeah, it could. If you train very well, the decisions should be the same. But it is unfair to compare one decision function with the other decision function, because anyway, both of the two decision functions are doing the same job. That is basically learning the input-output mappings. So you want to make your life easier to choose your activation function so that you don't land up in vanishing gradient problems or some pathological cases with differentiability, etc., that you may land up, that your network may fail during training or during testing, etc., right? So that is your choice. But the final decision, given the input and the output, irrespective of the kind of activation function, the network should be able to learn in principle. But because of practical issues such as vanishing gradient problems, etc., you would want to make life easier by choosing appropriate activation functions of your choice.
The next question, for neural network application purpose, what else has to be learned other than your coursework?
I think the best way is practice. Like, I can teach you a cooking recipe. Unless you try the recipe at home and see how it works, you will not be able to appreciate what is happening, right? It is as simple as put in this way, right? So, of course, in the course, it is impossible because we don't at the moment have such a sophistication where we can grade your assignments through, your software codes electronically, like a machine doing your grading of your assignments, your software code. We are not that advanced at the moment. But the best way is, after you learn the concepts, you basically think about an application like a speech recognition problem, or an image recognition problem, or an object recognition problem, or a segmentation problem. There are plenty of these data sets, for example, in UC Irvine data sets, etc. So you can take those data sets and play with it. Or if you're even electronic savvy, hook up certain smart devices, or any device. If you're electronic savvy, plug in those devices into your power systems or your water systems or whatever you think of. Extract the data from those devices, right? That is from your sensors, and you have rich data there. Then you exercise the problem. For example, if you were to learn the behavior of how your water usage is at home, and you want a neural network driven a water regulatory system for watering your garden, and to optimize the usage. If you're savvy with electronics, you can do that yourself. So that's the best way to apply the techniques you've learned in the course to actual practice, right? So I think I suggest that you try this, and it is very useful. And if you're doing research anyway, you play with data, because once you play with the data, you exercise a theory, or you develop a theory and then play it on the data, or you have the data and you work with a theory that works with the data, and then you generalize things. It depends on what your applications are. But I suggest that this is a very practical area, so you should experiment. You should experiment with data, but with a firm understanding of the theory. Yeah.
The next question is, what is the purpose of optimization algorithms?
I mean, this is it's a naive question. If I asked you want to go from, I don't know which part of city from India you are from. Let's say, I'm assuming from your name that you are from Tamil Nadu, but you could be somewhere else also, right? But let's assume. So you want to go from one part of Tamil Nadu to other part of Tamil Nadu, and what do you want to optimize? Let us I give you just have X rupees with you, or you're constrained on time, you're constrained on these things. So you put a lot of constraints, right? So with all these constraints, you'll have to optimize. So let us say you are constrained on money, then your mode of transportation would be restricted. And within the mode of transportation, given the traffic and other conditions, you'll have to optimize. Therefore, in real time, in our life, we always optimize. We may not do mathematical derivation, but we naturally optimize, right? If I have I can choose I want to avoid traffic, I choose shortcuts, right? I want to avoid traffic lights, I choose shortcuts, and maybe that may not be optimal for my fuel, but my time may be saved in some sense, right? Things like this. So you need optimization in everyday life, from cooking to going to work, or being at work, or doing things efficiently. You need optimization, including passing the course. I'm sure you would have to optimize carefully. Yeah.
Next question is on which programming language is best suited for implementing neural networks. I'm confused between MATLAB, Octave, and Python, and also R.
I suggest the modern trend is, you can use MATLAB. MATLAB has a good, so first, I mean, if you just want to test a simple algorithm to work, then I think, or, you do some research problem, you come up with an algorithm and you want to use the built-in functions, I think MATLAB is a very good first cut, a first step that you would take to check the veracity of your algorithm and all that. Beyond that, if you want to get a little more sophisticated, Python, people would like to use Python, or also because you have optimization packages, etc. And an ideal way would be to have a C wrapper that uses some built-in functions that can interface with MATLAB and Python, etc. So it really depends on what you want. But once you train, the main thing is training with all these algorithms. So the moment you train them, and you have the parameters extracted, then you can always use an embedded system or any other firmware or hardware that you can basically exercise on your testing set. So I believe that that's sort of a detail there. But yeah, MATLAB, because it already has functions, but I really like you to build these functions from scratch so that you understand how it works, right? Maybe the backpropagation is already there in MATLAB, but if you code it yourself from first principles and compare against what MATLAB provides you, you would have understood and exercised your knowledge of the algorithm. And this is very useful, particularly from research perspective. But if you're just a lay user and you just want to try how backpropagation works, use a tool from MATLAB or Python. That solves your problem.
So where can we get data sets?
So Amrita is just typing the URL where the data sets can be obtained. So this is a good URL. I think even for research purposes, people use this this URL to compare against algorithms. So I strongly encourage you to do that. But if you are a little more savvy, you would, and you are interested in building practical applications, basically plug in your sensors to your favorite system, water monitoring system or anything, and then extract the data from there and then try your algorithms using MATLAB or R or Python. C would be more difficult in terms of building all these functions from scratch, but if you're savvy with software and you like to build your own tools, you are encouraged with that route as well.
What are the major applications of neural networks in mathematics?
I mean, these days, I think as I mentioned to you in the introductory lecture or introductory slides, automated theorem proving has picked up momentum. I mean, there are, like for example, I have a sophisticated theorem that I know I work through many cases and there's a strong conjecture that it is right or wrong in one way or the other. Can I come up with constructs starting from how, like for example, I learned geometry, right? I start with basic axioms of what a linear pair is, and then build these axioms, what a ray is, how an angle is formed and how a plane is formed, etc. I build these constructs from scratch. So once I have all these axioms, and then I link these axioms in a way that I can establish relationships between them, right? I have a linear pair, then I have the angles in some of the interior angles of a triangle. Now, can I establish relationship between sum of interior angles of a triangle and then a linear pair? I mean, these relationships are what we're trying to bring in, and associations. And this is an area which is very fertile, where neural networks can help in automated theorem proving. I mean, this is a simple exercise to start with, but there are very sophisticated theorems, such as even like the four-color theorem proving, right? So this is, these things, people are beginning to think how to even set up a neural network to do these type of tasks, right? I think these are applications. But neural networks itself is a mathematics area, right? To me, it is nonlinear signal processing, and nonlinear signal processing stems from basically your stochastic processes, your optimization theory, harmonic analysis, and other areas. So neural networks is itself applied math, which can be used for theorem proving in most mathematical areas, if you think about. So people are thinking in this direction. So, okay.
I found out computer experiments from Simon Haken's book. Should we try that assignments?
Sure, you are welcome. In fact, those assignments, sometimes I've assigned these problems when I teach this course in IAC. Also, because the strength in IAC is not as much as what we see in NPTEL. We have about 30 students or 25 students, so we can give those data sets, and then they sometimes submit 25, 30-page reports as part of their homeworks, and which the advisor can grade, the instructor can grade these homeworks. But unfortunately, we don't have such a mechanism here, as I told you, with NPTEL, that a machine can grade, because it's a massive scale because of large number of students taking the course. So one way that at the moment to overcome that limitation that you can augment is basically try the exercises from Haken's book or any other book, or your own data sets that you're comfortable with. As I mentioned, I gave you the URL. You can look for other URLs, get the data sets, and then try this on these data sets, and that will really help you from your learning perspective, which is outside of the scope of the homeworks and the examination you will see from NPTEL.
The next question is on, can we use TensorFlow to implement neural networks? Also, where can I get trained to use Google Colab? Is Google Colab really useful?
Frankly speaking, I have not tried these tools myself. Um, um, so I cannot comment about these tools. So I mean, definitely Google Colab is something which is new to me, which have people may be comfortable or familiar with these tools. So I suggest you look through the fora, that is on software fora where people have discussions on these. And if you find something useful, then I suggest you can try. But in academic world or even in the industrial R&D world, I think reasonably people use MATLAB, Octave, Python, and R, some of these packages, and sometimes they code with R, with C, and they interface with these tools using um, appropriate interfacing software. So I cannot answer your question. So it depends upon your application, the benefits or limitations of the tools that you have listed there. So I suggest go through the Google groups and the appropriate fora, and then you may find those discussions. And there are also um, folks that teach these packages, these software packages themselves, and you can go through those courses or those I mean fora or the courses which talk about the software packages, that you can extract the information from those courses and then see if it is useful for your purpose. So unfortunately, we don't cover those packages part of this course as part of this course. So I cannot answer your question in affirmative.
Next question. An application where signal is processed using neural networks which solves a real life problem.
Okay, plenty of solutions. I mean, plenty of problems and solutions. Okay, imagine the following. I give you a speech signal, right? So let us, we are, I mean, this application was built at least 30 years back. I'm talking about isolated speech recognition using neural networks, right? So I speak 1, 2, 3, 4, etc. And I want to use these words. So I speak 1, 2, 3, 4. Somebody else can speak this with a slightly different accent. There could be also gender-based variations, right? A male speaking the same words versus a female speaking the same with with their pitch, right? So these are all signals that you actually capture. But now if I were to give you a machine which recognizes, for example, I speak 1 or my student Amrita speaks 1, the door, the digit 1 should appear on the screen, for example. So how do you make a network learn this, right? You see the signal is coming from speech, but the action is happening on the screen where you have a 1 displayed, irrespective of who is speaking this word. That's the simplest application. Or recognition of commands, right? I have an automated home system where I mean, I can open the door that should recognize my voice or the inmates of this home and nobody else. I can create such a system. So I can think of plenty of applications like water monitoring system, echo cancellation. These are all traditional applications, but not just this, even modern day applications. Like I sing something and I want a text out of that, right? Or I talk about I talk about cat, and the image of a cat should appear, or do something with cat, right? These are all real applications dealing with speech, text, images, etc. They are all signals in real time. I mean, real life signals that you want to process them using neural networks. So it is all they are all real life problems. I hope it addresses your question. It is a practical course. It's not something that we are dreaming in the abstract world. Yeah. But I'm happy we have quite a lot of questions. Yeah. But I'm also curious if you people are bowled out because of the AI era, or you really like these problems in neural networks. I mean, there are two kind of people. One that go with the buzzwords, like your nano or AI or something else, and then want to catch up with these buzzwords, and the others that are really interested and passionate about the area itself. I think I would like to stress on the latter than the former, so that you really like to do something and you want to do something uh, in this field, and you're really interested in this. Yeah,
Next question, will neural networks dominate in the future?
I suppose so, because a lot of mundane tasks which people are doing right now can be automated. I'm pretty confident that in the next 10 years to 15 years, there will be dramatic changes in the way AI systems will pave way towards learning relationships, associations, and then eventually leading to decision making. For example, imagine you have a highway system, right? I have a freeways, I have 6 lanes, and I'm going in my vehicle, truck or a car or SUV or whatever it is. And today we have these um, humans sitting there, collecting the toll or whatever. We may not, or taking cash, and then you letting the toll gate that you can cross. Tomorrow we may not, we may be cash, we may not deal with cash, right? We may have smart cards and these things which will allow us, as we navigate through these freeways, automatically the gate opens as long as we have a valid entry. Otherwise there would be a robo there where we have to answer certain questions, and only if it is satisfactory we are allowed to cross the toll gate. Otherwise, there will be a police officer sitting there basically, to, in the event it fails to deal with the situation, right? And automatically the money gets deducted. Automatically your number plate, name plate will be visible to the system, and it is all self navigated. And I'm also confident, at least in certain countries such as in the US, Canada, etc., that you have these driverless vehicles. I mean, particularly if you have streamlined freeways and very streamlined freeways, you can drive without a driver. I mean, it's a self-navigating vehicle, and this vehicle can have the information where the nearest toll booth is, and everything is very well networked, that there is no room for uh, errors, right? And this is some of the this is one of the major advantages. For example, I'm giving you an instance in a traffic navigation system. Similarly, in drug discovery, yes, you don't have to sit down and work with a lot of experiments to figure out what compounds work well. So a lot of your outcomes from your chemistry experiments, that information can be fed into this AI system, where it processes quickly to figure out what compounds align well to what, and you may come up with new discoveries in terms of drugs. And again, for agriculture, precision agriculture, right now we have to monitor these plants in the watering, the cycles, manure, fertilizer, etc., and also the recycling of crops. And a farmer doesn't have to struggle so much. And if you have network waterways, this much of water is required for this particular field, and this much of manure is required for this particular field. So I think precision agriculture, coupled with intelligent waterways systems, etc., I think everything is all interconnected, right? So I think thinking about IoT and NN, neural networks, I think that's the right direction. That makes our life easier, right? That's why we want to bring in this automation. But you may question that you lose jobs from human jobs perspective. But the human can be used for better things than maybe mopping the floor and doing things. I mean, of course, I would like to do this for exercises. To exercise my body, I want to mop the floor. But if I really don't want to do that, I can employ a robo at the time when I'm really busy, that the robo can do it for me, right? And that's where neural networks can have its role that we control. Yeah.
The next question is, can we use neural networks for controlling a process in an industry for using as a controller?
Yes, yes, yes. We discussed these applications, right? For system identification, control. We talked about all these problems, so you can use for this purpose. Yeah. We talked about it in one of the modules. We give a block diagram, etc. So yes, to answer your question. Um,
Next, please put some light on neural computation.
it's a very broad area. So So I think, okay, let me give you this perspective. So the way you think about AI systems is one is I think I mentioned this in my introductory slides. There is one area where you think about neuromorphic computation or neural computation, where you think about how the brain does computation. I mean, you get these information from biology and biological studies, and you have the experiments which will reveal certain information, and you want to encapsulate that information within a mathematical framework to explain the behavior you see in empirical data, right? And that's the neuromorphic system, and you build systems around that, inspired by biological cues. The other way is, you say it's a neural network because it has what you call the ingredients with an activation function, and with a neuron that you define the way it is a mathematical neuron, and you do computation on that, right? And that computation is purely artificial, and therefore it's an artificial neural network computation, or neural computation which is on artificial means, which is nothing related to biology, but has some links and some cues that are derived from biology. But people are going in both the sides. One is this side where you talk about statistical, many things in artificial neural networks and automation and things like this. The other field is basically understanding how biology works, right? How nature works, like how the brain stores information, how efficient memory and computation happen in biological systems, and then can we bring that information. Um, of course, you have to bring in mathematics because that gives you the power of expression of your thought or observations that you see in science, right? And this is the other area. So I think neural computation happens in both the sides. One through biological system, and then getting it into mathematics, and to explain how nature works, and then building systems attuned to nature. The other way is, completely artificial neural networks for all the applications I discussed, like traffic navigation system, waterways, etc. You don't need any biological thing there. Maybe you are faster working with a mathematical algorithm and learning algorithm that can solve your task. Okay, we are almost an hour done, so we can take last few questions, maybe a couple of them, and then wrap this up. Okay, I see the thank you. So welcome. Yeah. So here's one question. This question may seem different.
Can we model our brain using neural networks?
You are asking tall questions. It's like, can I create the Earth? You cannot create a simple, I would say, a virus or a bacteria. Right? You have this, artificial a bacteria, like, can you create a bacteria? You cannot. Or can you give life? You cannot. So modeling the brain is a tall task, a really tall task. There are so many functionalities in the human brain. It's a tall task, but the hope is we get close, at least close. I would say even if you get to 10 to 20% of what it is, I think it's a huge accomplishment. That number is still far from reality. And if you think about how efficient we are in terms of using our brains, I think some of the brightest scientists may hardly use 5% of their brains or 10% of their brains. And it is that vast reservoir that you have that is still dormant, unexplored. So I don't think, yeah, he is asking this question in a philosophical perspective. Yeah, we are on this task, but far from reality. Yeah.
The next question is on, can you explain regularization in simple words?
Regularization is a very simple idea. Like, for example, I tell you that I want to go. It is basically putting constraints on to a cost function, and these constraints are regulatory constraints. What do you mean by regulatory constraints? For example, I want to go from point A to point B, and I want to optimize the distance to going from point A to B. There are many paths. I want to optimize this distance. But as I'm going to different paths, I may be restricted in terms of my speed because I may have a natural speed restriction on each of the lanes. But I'm driving my vehicle, and if my vehicle has to be has to drive well, or I have to use fuel, I have to bring in fuel efficiency. I want to regulate my speed. I don't want to go too slow. I don't want to be too fast. So that is the constraint I want to put. Now, given these constraints and given the cost, that is, I want to minimize the distance, what is the best solution that I can think of, right? And that may give me that these are the so when I put these constraints, they become regulatory constraints, and this problem is basically a regularization problem. I want to solve an optimization problem subject to these regulatory constraints. And often, sometimes putting these regulatory constraints can make an ill-posed problem a well-posed problem, and I think that we will talk about in the next set of lectures when we talk about regularization ideas. Okay, so we are 5 minutes done with this. So of course we would like you to reserve your questions. Please post these questions to the TAs. They'll be happy to address these questions, and then you can write to us. We will be having these interacting sessions every month. So I suggest that you plan these questions a priori, and I don't require the questions a priori. So you can plan these questions and then come up with these questions, and we'll be happy to take these questions like it is in Man Ki Baat. Okay. So with this, I would like to end this session. It was great interacting with all of you. Wish you all the best, and I hope you find these courses interesting. And please leave your likes and your comments on the YouTube videos, and we look through these to get the feedback as to what is happening with your learning experience on the other side. Okay.